webinar series. On behalf of the ISPRS TC V Working Group 4, I welcome you all to this webinar. And today we are having the fourth webinar of the series of 6 webinars. And one of the most important in this series. And to deliver today's lecture, we have with us Dr. Mahapatra sir, who is the Director General of Meteorology at the India Meteorological Department and also the third Vice President of WMO. I welcome you, sir. We know, sir, how busy your schedule have, and we are extremely thankful to you for kindly accepting our invitation and sparing your very valuable time to deliver this talk. Sir will be speaking on geospatial technology for effective disaster risk management. So before I hand over the session to sir, with your kind permission, sir, I would like to take a couple of minutes to introduce you. Of course, DGM sir does not need any formal introduction, but it's an honor for me to introduce sir. So Dr. Mahapatra sir is the Director General and also the third Vice President of the WMO. Recognized as the Cyclone Man of India, he is renowned for his outstanding contributions to the field of meteorology, particularly in the domain of cyclone forecasting and disaster management. With a distinguished career spanning over 3 decades, Dr. Mahapatra sir has been instrumental in transforming India's weather forecasting capabilities. His leadership has significantly enhanced the accuracy of cyclone predictions, storm surge modeling, and early warning systems, contributing immensely to disaster preparedness and resilience in India and abroad. Under his leadership, IMD has adopted cutting-edge technologies, including satellite remote sensing, numerical weather prediction models, and artificial intelligence for more reliable and impact-based forecast and risk-based warning services. Sir has given equal importance on outreach and warning dissemination system as well, and his contribution towards development of common alert protocol by National Disaster Management Authority led to extension of the outreach with warnings reaching to every mobile holder in an affected region. So the timely and precise forecast given by his team, led by Dr. Mahapatra sir, enabled effective evacuation measures and saved thousands of lives in major cyclones. His pioneering efforts have positioned India among the leading nations in cyclone forecasting and early warning dissemination. A distinguished scientist, Dr. Mahapatra sir has authored more than 200 research papers, articles, and book chapters in reputed journals and has contributed extensively to the development of regional and global meteorological strategies. He has also represented India at various international platforms, collaborating with organizations like the WMO and the United Nations on issues of climate resilience and disaster risk reduction. And in recognition of his remarkable contributions, Dr. Mahapatra sir has been honored with several prestigious awards, including the Scientific and Technological Activities Commission Outstanding Service Award 2025 by American Meteorological Society, a WMA Award for Disaster Risk Reduction, Young Scientist Award 2008 by Ministry of Earth Sciences, IMD's Award for Excellence in Weather Services, and many more awards, and honorary DSC from several universities, fellowship by many professional societies, etc. As the chairman of more than a dozen international and national scientific committees, he remains a guiding force in the field of meteorology, mentoring young scientists and inspiring innovation in the weather forecasting. So with his unwavering dedication in safeguarding lives and livelihoods, Dr. Mahapatra sir continues to make a profound impact on climate resilience, disaster management, and sustainable development in India and beyond. So with this brief introduction, I once again welcome you, sir, and request you to deliver the talk. Over to you, sir.
So thank you very much, Dr. Kundu, and my dear friends and colleagues participating in this webinar. Namaskar. Good evening to all of you. At the outset, I express my deep gratitude to ISPRS and Northeast Space Application Center, Dr. S.P. Aggarwal, and all colleagues for giving an opportunity to present this very relevant talk on geospatial technology for effective disaster risk management. My talk will be mostly dedicated towards the disasters which we experience in India and the various approaches, methods, tools, and technologies utilized for that to reduce the risk. To begin with, if you just look at the various types of natural hazards which affect India, you will find that India is such a country where you would have all types of hazards. You have the earthquake, you've got the heavy rainfall leading to floods and lack of rainfall leading to droughts. You have got the tropical cyclones, then you have got the excess rainfall and deficient rainfall years, in terms of flood years and drought years. Also, you will find that occurrence of the thunderstorms. It is another killer. It kills people in large number. About 3,000 people die in the country every year because of the thunderstorms and associated weather like lightning, squally winds, gusty winds, and hailstorms, and of course the heavy rain sometimes. We also experience the tornadoes and hailstorms apart from the thunderstorms and lightning. Over the period of time, there has been significant improvement in monitoring and detection. We have been able to detect each and every synoptic scale weather events like, say, low pressure systems, depressions, cyclones, etc. But when you talk about the mesoscale severe weather hazards like, say, location-specific heavy rainfall or location-specific thunderstorms, lightning, or hailstorms, it is still challenging, though we have improved significantly in recent time for detection of these highly localized severe weather events and their predictions. Now, if we just look at the weather systems which cause the various types of hazards in the country, you will find that there are two major systems. One is the monsoon, which prevails during June to September, and it causes heavy rainfall and also thunderstorms during monsoon season. You can have the floods and droughts, and all these can occur anytime in different parts of the country during June to September. Then we have the pre-monsoon season, that is April, May, June, especially before the onset of monsoon, when you have got the cyclones developing over the Bay of Bengal and the Arabian Sea, and these cyclones affect the various countries in the North Indian Ocean. In addition to cyclones, we also experience the thunderstorms, especially over eastern India, northeastern India, and peninsular India. And these thunderstorms are very furious, especially over eastern and northeastern India, and they are called as nor'westers or Kal Baisakhi. We also have another season after monsoon, which is called post-monsoon season, October to December, which is otherwise called as northeast monsoon season. It causes very good rainfall activity over southeast peninsular India. And during this season also, there could be development of the tropical cyclones and depressions. Actually, the cyclones and depressions are more frequent in post-monsoon season, October, December, compared to the pre-monsoon season, April, May, June. And during monsoon season, June to September, we get monsoon lows, pressure areas of the head Bay of Bengal, and they move west-northwestwards along the monsoon trough, giving copious amount of rainfall to the south of this monsoon trough. We also have another system called as mid-tropospheric cyclone, which developed over the western part of the country, especially Gujarat and adjoining northeast Arabian Sea. It also causes very heavy rainfall activity over the region, leading to sometimes the floods. During the monsoon season, sometimes you get very deep offshore trough near the west coast. And this is a trough in the pressure. Due to this trough, sometimes the pressure gradient becomes very high and winds become very high near the west coast, and it leads to the heavy to extreme heavy rainfall activity. And this heavy to extreme rainfall activity during the monsoon season in the hilly regions are very disastrous, as it leads to landslides and the floods. Sometimes there are certain cloudburst phenomena occurring in the hilly regions where the amount of rainfall increases and becomes more than 10 centimeters per hour. Then we call it as the cloudburst. We also have the easterly waves moving along the equator. It affects especially the northeast monsoon, and we get very good rainfall activity with association of the easterly waves. And sometimes embedded with easterly waves, we get low pressure systems, depressions, or cyclones. We also have the winter season, that is January, February, or even sometimes December to February, you can say. During this season, we have got more frequent western disturbances, which move from west to east, and they affect the northwest India, especially the hills of northwest India, like Jammu and Kashmir, Himachal, Uttarakhand, experience the heavy snowfall sometimes leading to avalanches as it occurred 15 days before this year in Uttarakhand and Himachal Pradesh. We also get the fog, this blue color, what you find in the Indo-Gangetic plains. This is the fog which occurs in the month of December to February. The frequency and intensity is maximum in the month of January. The visibility becomes almost zero, and it affects the entire transport system, including surface transport like national highway transport or the railway transport, and also the aviation transport. Most of the airports gets affected in northern India because of the fog. So considering all these things, these hazards, the meteorological hazards affect our life and livelihood and also the critical infrastructure. So many people died in the previous years. If you see the 2 decades before, many people died because of the cyclones, heat waves, heavy rainfalls, etc. But nowadays, the number of deaths have reduced because of the improved early warning system and early action developed by the state and disaster management authorities and central disaster management authorities. There is complete cohesion in the various agencies in monitoring, detection, analysis, forecasting, early warning generation, presentation, dissemination, and after that, the preparedness and preventive actions by the concerned authorities. So these are the major critical infrastructures which get affected because of the various types of natural hazards. And therefore, we take care to provide early warning to all these major critical infrastructures. Say, for example, disaster management organizations, cyclone and flood shelters, aviation, power grid, highways, power and energy resources, defense, dams and reservoirs, petroleum, tourism, sustainable environment development, agriculture, transport system, including marine, then water supply, all get affected, and all these sectors get the early warning for disaster risk reduction. Now, when I talk of the disaster risk reduction, it has got various components like the pre-disaster, during disaster, and the post-disaster. And during all these 3 phases, you need the response. And the response is generated based on the multi-hazard early warning system. So multi-hazard early warning is provided by early warning agency based on which the response actions are taken off in disaster time, pre-disaster time, and the post-disaster time. Of course, after that, during post-disaster, we have got the recovery actions, and hence the mitigation, prevention, risk reduction are taken off with the help of the multi-hazard early warning system. To carry out this entire process of disaster risk reductions, there is national policy in the country, there is National Disaster Management Act, we have got National Disaster Management Plans, we have got national guidelines, we have got institutional mechanism also. At present, if we just look at India is self-reliant with respect to weather and climate services in terms of contribution to economy, development of the system and infrastructure, socio-economic applications, and disaster risk reductions. In terms of forecast accuracy, you will find that the service delivery, it is at par with leading centers of the world. So it is impossible because of the investment in technology in the recent decades, and hence the improvement. Now let us look at our hydrometeorological hazards. When we chase these hydrometeorological hazards to minimize the risk, an institutional mechanism should be in place. And in India, we have got an institutional mechanism. There is overall coordination of the disasters is taken by Minister of Home Affairs. Under the Minister of Home Affairs, we have got designated nodal ministries, disaster specific. Say, for example, IMD is responsible for meteorological disasters, Central Water Commission is responsible for the floods, and Minister of Urban Affairs for urban flood, Geological Survey of India for the landslides, National Center for Seismology is for earthquake, like this. Then we have got National Disaster Management Authority in the country, which coordinates the policy making in the country for management of the disasters. Then for top level decision making during, before and after disasters, we have got the Cabinet Committee on Security and National Crisis Management Committee, that is called NCMC, headed by the Cabinet Secretary. To support the both organizations, we have got National Executive Committee headed by the Home Secretary in the Ministry of Home Affairs. And this NEC is supported by Armed Forces and Central Armed Police Forces. We have got National Institute of Disaster Management for capacity building, which helps the NDMA, and we've got NDRF, that is National Disaster Response Force, which takes action during and before and after disasters, which works under the NDMA. Then we've got state government union territories, state governments union territories, where we have got the state level disaster management authorities, district level disaster management authorities. We've got state disaster response force, which work towards this direction of disaster risk reduction. So when you think, therefore, the components of DRR in India, we have got hazard and risk analysis, preparedness, early warning system, prevention, and mitigation. And when I come up with the components of early warning system in India, it starts with the monitoring, analysis, and predictions, then impact-based forecast and risk-based warning, warning generation, presentations, and disseminations, then coordination with emergency response units at state and central level, and post-event review, pre-season exercises, public education, and outreach. Now, if you look at the role of various agencies, there are dedicated agencies, as I was telling you, and now I will concentrate on the role of IMD, or India Meteorological Department, in the Ministry of Earth Sciences for Disaster Risk Reduction. IMD is the nodal agency to provide the weather and climate services and provide the advisory and warning for the meteorological hazards. It includes the cyclones, heavy rainfall, thunderstorms, heat waves, cold waves, lightning, etc. And the target is that no weather hazard should go undetected or unpredicted, and we provide therefore hazard monitoring and assessment. Then we provide early warning or mitigation. The warning against any hazards should be accurate with reasonable lead time and trigger the response actions from the disaster managers. We also provide the technical support in assessing the vulnerability and the risk. Based on the past historical data, we can assess the vulnerability, climatological vulnerability. Of course, real-time vulnerability is also assessed. The technical support is provided for preparedness and planning, and also for management of natural resources from the disasters, like, for example, management of agriculture or water resources like dams and reservoirs, energy resources, etc. So to carry out all these, IMD has got a vision and a mission. The IMD's vision, as I was telling you earlier, is that the meteorological observations forecast for optimum operation of weather-sensitive activities. And no weather hazard should go undetected or unpredicted. Accurate warning against the hazards with responsible lead time, with reasonable lead time, so that it can trigger response actions by the disaster managers and public to save life and property. Then, of course, impact-based forecast and early warning for all types of weather has been introduced in 2019, and target is that more granular information should be provided with respect to impact and hence the risk. So to carry out, therefore, there are various pillars in IMD. One is the observations and monitoring of various types of weather events. Second one is the numerical modeling with the help of the high-performance computing systems. We run about 7 models in the country to provide the forecast. Then the forecasting. Forecasting is not the direct model output. Here, based on various models, we prepare the multi-model ensemble for dynamical statistical post-processing, and then the knowledge, experience, expertise of the forecasters are taken care to evaluate in the numerical output. So therefore, finally, the forecast issued to public and disaster managers and stakeholders is the objective consensus derived through a decision support system from an array of numerical weather prediction models and the observational network, which is modulated by the human knowledge, experience, and expertise of the forecasters through a video conferencing system. Every day at 10:30, all the forecasters from 32 centers in the country confer with each other and take a decision about the weather systems, the hazards, and its impact according to the forecast and warnings. Then we have got the sectoral applications like sports. There are dedicated wings in India Meteorology Department to take care of, say, for example, specific sectors like aviation, marine, cyclone, thunderstorms, heat wave and cold wave, and flood forecasting, and so many. Then, of course, we've got severe weather warning for the specific severe weather. To carry out all these things, research and development is carried out globally and also nationally. In IMD, also people carry out research and development and coordinate with various R&D organizations in the field of meteorology to gain the new knowledge which can be utilized to service. So therefore, if you just look at IMD services, you will find that at present we are providing forecast at the location specific level, then block level, district level, river catchment level, and meteorological subdivision level and state level. And forecast is now impact-based forecast up to 5 to 7 days for all types of severe weather. And you can find out various sectoral applications as I have written here. Perhaps no sector is left out at present, which is not getting the forecast. Almost all sectors are getting forecast from India Meteorological Department. Now, if I tell about the integrated multi-hazard early warning system, how does it work? You will find that the basic principle of meteorology is that it is an initial value problem. That means if you know the initial status of ocean, atmosphere, land surface, then you will be in a better position to predict the weather. So therefore, globally, the attention is that to maximize the observations. If you can have good observations, then you will have the good forecast. So we try to improve our observations in 3 dimensions, like the surface-based observations utilizing the automated weather stations, basic departmental observatories, etc. Then also we have got the balloons released into the atmosphere with the help of the hydrogen gas or helium gas. Then sensors are also released, and these sensors provide the information about the weather parameters like temperature, humidity, pressure, wind speed, wind directions, etc. Then these are called the RSRW, radio sound and radio wind. Or sometimes without sensor also balloon is released and is followed with the GPS. Therefore, we get very accurate wind informations. Then we have got the Doppler radar, with the help of which we get the information in the country. Now we've got around 40 radars and 85% area is covered by the radar at present. Then we've got satellite. Indian Space Organization maintains the satellite network. At present, we've got 2 satellites which provide the observations in terms of imageries and products and various data also. And all these images and products are made available every 15 minutes. And therefore, we get almost 48 products in a day, set of products. And all these provide us very real-time monitoring of the various types of weather systems. Then, of course, we have got special observations, like, say, for each airport has got observational network by IMD, and this is specific observation. So aviation weather, therefore, is also another set of observational network. Then ships. There are 206 ships which are recruited by IMD honorarily. They provide the information to us, and we appreciate them. Also, we've got the buoys. The meteorological buoys are the floating platforms in the sea, which provide observations with the help of the sensors, and data are transmitted with the help of the satellite inside, and we receive it and utilize in monitoring and forecasting. We also have the data from aircraft. Each aircraft is inbuilt with the weather sensors. So we get therefore the observations from the aircraft whenever available. So by that way, in the recent time, we also come up with the crowdsourcing. Anyone can report what is the weather going on in his place or her place, and that information is also utilized. So all these information, what I told in terms of the observational network, are digitized, and they are utilized in a DSS, decision support system, to find out what is the current status of atmosphere and ocean. We identify the low pressure systems, high pressure systems, other weather systems, etc. At the same time, all these data, digital form, are fed into a high performance computing system, and numerical representation models are run. And with that running of numerical representation models, we get the simulation of the current systems or current atmosphere, and we go in different time steps, we predict it. And there are different types of models there. But there are seasonal models to predict the seasonal forecast, followed by the monthly forecast by the climate model. We also have the numerical representation models and combination of the climate model to provide the extended range forecast up to next 4 weeks. Every Thursday, we issue that forecast. To follow up that, we have got the daily forecast up to 7 days at the district level, and the block level forecast for next 5 days, and location specific forecast also provided up to 7 days. So recently we have come up with a special scheme called as Har Har Mausam, Har Ghar Mausam, or the Mausam Gram, that suggests that wherever you click in the geospatial platform, you will get a forecast. And if you write the name of Panchayat, you will get a forecast, and the right name of the block, you will get a forecast. So by that way, you get forecast up to 10 days, every hour forecast up to 24 hours, then every 3-hour forecast up to 5 days, and every 6-hour forecast up to 10 days. So impact-based forecast early warning is provided district level and location-specific level up to 5 days or 120 hours for all types of severe weather event. Now, once all this modeling is carried out, so what we do actually, all this modeling provides the model output, and these are utilized decision support system to generate the forecast. Then it goes to end user by various communication means. Now, when I talk of early warning, there is a global initiative called as Early Warning for All, for United Nations WMO call, and role of India. If you just look at India is an active member of World Meteorological Organization and also helps other countries to improve the early warning. We act as a regional center to provide the advisories and early warnings to countries in South Asia, Southeast Asia, and the Middle East and North Indian Ocean. So we help the countries to develop this early warning for all. In our country also, we continuously upgrade our early warning for different types of hazards. So for this purpose, there is a disaster risk knowledge. There are 4 components for early warning for all. The first component is disaster risk knowledge. Based on the past historical data, we can develop the disaster risk knowledge, and here the role of geospatial technology comes up. If you've got data from different, it can be geo-enabled, it can be with the geo coordinates you can analyze, and geospatial interpretation can be carried out, and you can prepare the downscale information for each station, each block, each tahsil, etc. Then the second component is the detection, observations, monitoring, analysis, and forecasting of hazards. It's a real-time work which IMD does. The fast risk knowledge also is done by IMD, but it is also the responsibility of the concerned disaster management authorities and state disaster management authorities. We also prepared the climate hazard and vulnerability atlas, which caters to the requirement of disaster risk knowledge. We have got preparedness and response capabilities, that is building national and community response capabilities. So for this plan, response plans, as you know, that is prepared by NDMA guidelines, etc. And it postulates what are the actions to be taken, what do's and don'ts, etc. for the common people, disaster managers, and stakeholders. Then warning dissemination and communication, that is the responsibility of the telecommunication department in every country. And here also it works, and all of us know that how the warning dissemination has improved over the years. Now we've come up with the common alert protocol. So in the value chain, if you just look at weather observations to modeling to forecasting to severe weather warning and sectoral applications, there is R&D and there is technology intervention, and spatial technology or geospatial technology has the role everywhere, be it observations, monitoring analysis, or be modeling analysis, or be it the forecasting and sectoral applications. Because at present, if you want to provide the very granular information, the information for the common people, information has to be available in geo coordinate. Now let us look at, because of all this development in the country, what has happened finally. The outcome is that there is excellence in early warning systems. There is improved accuracy in last 10 years, 40% improvement forecast scale during the past decade compared to previous decade. There is improved confidence of disaster managers and general public. There is enabled disaster managers and public to minimize loss of lives and properties. Just like I was telling you, 10,000 people died in 1999. And 2023 Viparjaya cyclone, death was 0 in Gujarat, and Dana cyclone 2024, death was also 0 in Odisha. So it demonstrates how the country has come up over the years in the past 2 decades to prepare the disaster management policy, plans, guidelines, institutional mechanism, early warning systems, and to develop the technology, including geospatial technology, which is helping the country to minimize the losses of lives and properties. It has been highlighted and appreciated globally also. So this is an example in the below that you will find out how the loss of life has been minimized in the recent time, even to zero in 2024 Dana cyclone. Similarly, in case of heat wave, also if you look at in 2015, 2,000 people died in the country because of the heat wave. After that, seamless forecast of heat wave was introduced, and accordingly, heat action plan was developed in the country, and combination of both helped to minimize the losses. There are only 4 deaths in 2020 as compared to 2015. Similarly, if you compare the heavy rainfall losses, I will tell an example of the 2013 when 4,000 people died in Uttarakhand because of the heavy rainfall induced landslides and flooding, etc. Whereas similar flooding and heavy rainfall occurred in 2021, but only 30 people died in Uttarakhand. That is success story, but still 30 people should not die. Also, we should try for minimizing further the loss of lives. So this is just an example of cyclone forecasting warning process. You will find that there is a seamless forecasting system from 15 days ahead. We provide the genesis forecast and other forecasts. So we have the pre-genesis forecast and customized forecast information of depressions and issue of special bulletins starts from low pressure states unlike the other countries in the world. So we have got a very systematic approach with respect to severe weather hazard with the help of the technology. Now, this is just an example how the geospatial technology is being utilized to provide the information to the people and disaster managers. On the left-hand side, you'll find that black line is the observed cyclone track, and red line the forecast cyclone track for cyclone cyclone Taute in 2021. You will find that how accurately the track intensity, landfall point, and time are being predicted, and also how the geospatial technology is being utilized to provide information in very granular manner. The left-hand side two diagrams are available in WebGIS in IMD's website. The right-hand side, you'll find the impact of the cyclones in terms of floods, winds, and surge. These are all prepared every village level, even in the coastal districts. And the username password are provided for this dynamic composite risk atlas to the block development officer and tahsildars, and they can open and assess the hazard, its impact. We also provide a risk forecast in terms of that. What is the risk towards agriculture? How much land will be inundated? How much loss will be there to the agriculture in terms of rupees? So this risk forecast helps the government to release money before the cyclone hits the coast, and therefore you can say that there is risk financing based on the risk forecast in the country. So this is the improvement. You will find that accuracy of landfall point has improved by 40 to 70% during 20 to 24 compared to 15 to 19. And there is forecast accuracy, track and intensity improved by 20 to 25%. So this is possible because of the intervention of various technology, and the service has been improved because of the geospatial technology. I will come in details a little after. So this is another example of monsoonal heavy rainfall warning skills, how the heavy rainfall warning has improved. And at present, the forecast accuracy in 2024 was 83%. Probability detection of heavy rainfall 24 hours ahead was 83%. So, and if you look at the false alarm, it was quite less than 15%. So this type of warning for heavy rainfall has helped to minimize the losses due to floods, landslides, etc. Now let us take third example. This is the heat wave. The top one is the heat wave climatology based on data of 1961 to 2020. You'll find the entire northern India, central India, and northern peninsula gets affected by the heat wave conditions. If you look at the heat wave scale, yes, it is quite good. Day one scale is 95%. So that means the probability of detection is 95% for day one. Day two, it is 88%. And if you look at day 3, it is 77%. By day 5, it is 60%. So there is a good skill in predicting the heat wave. It's like that also cold wave. As a result, there is early action based on the heat action plan developed. And this type of maps, what you find, these are available in real time in WebGIS in IMD's website. Or every day you can find out the temperature distributions, departs from normal. You can find changes in past 24 hours. You can find out the warm night conditions. You can find out the humidity conditions, wind conditions. You can find out temperature humidity index. You can find out the percentile of the value which has occurred today and its forecast in next 7 days. So all these are helping to strengthen the knowledge and capability of the individual and the disaster managers. This is another example of the thunderstorm. You can say that we provide thunderstorm forecast everywhere in the country in short range forecast, that is 2 to 3 days in advance, and also provide nowcast every 3 hours. And you will find that how the forecast accuracy is improved over the years. Here we have just plotted a diagram from 2016 to 2024. In 2016, you will find that POD was just 31%, and 2024 POD is 88%. You can just imagine how the country has developed over the years. And on the top diagram, you will find out how the geospatial technology is being utilized in decision support system to analyze by layering the information observations, modeling, and accordingly by making a decision about the occurrence of the thunderstorm lightning and its forecast for next 3 hours or next 24 hours. Now, coming to this role of geospatial technology, I want to say that the forecasting in IMD is completely based on DSS, decision support system, which is geospatial in nature. We've got weather monitoring forecasting, we've got flood monitoring, drought and water management, disaster response and damage assessment, short and risk operations, climate and long-term monitoring, etc. All are being carried out globally now in India, also utilizing the space technology. Now let us look a little more about space-based observations for weather monitoring and forecasting. The space-based observations are used for monitoring of weather hazards, then physical understanding, development of climatology, hazard mapping, and you will be happy to know that 90% of data which are utilized in the numerical regression models are from satellites. Satellite-based informations are also used for nowcasting to climate modeling. And study shows 25 to 30% improvement in numerical regression model forecast accuracy by the satellite observations. And there are some samples are shown here, like the cyclones, dust storms, thunderstorms, lightning, etc. And further, Indian Space Organization and IMD have come together to develop a tool called as RAPID, RAPID, which helps you to find out the various types of cloud pattern and whatever information you have got in the satellite in a geo coordinate. You can find out your area and you can find out what is the depth of cloud, what is the cloud of temperature, what is the water content of the cloud, how the cloud is developing or evolving, and how the cloud is moving. All this information helps, especially in the nowcasting. And also there is a provision in this RAPID to overlay the other parameters like say radar or the numerical regression models. Now, if I look at the application of satellite products for weather and climate forecasting, you will find that it has the utility in weather and climate monitoring and forecasting, weather and climate modeling, the climate services like climatology or climate variability. It also has the application in environmental monitoring, like say PM10, PM2.5, aerosol or aerosol depth, etc. Then sectoral applications in agriculture, hydrology, aviation, marine, urban, power, health, transport, tourism, everywhere you can find out the role of the satellite. Then DRR, of course, cyclone, droughts, floods, thunderstorms, heat, cold wave, etc. Everywhere we utilize the satellite and geospatial information to assess the current status and provide the forecast. So when I say the forecast, we have got various types of models starting from nowcast to seasonal forecast. We have got the nowcast models, then regional models, then global models, and of course, we have got the multimodal ensembles. So what we do actually, we do not depend upon one model, we depend upon the array of models and develop a multimodal ensemble looking at the past history of the models. The better model is given more weightage and worse model is given the less weightage. So this is the state-of-art modeling technology, which is utilized by IMD for various scales of information. And at present, based on the accuracy, we provide 5 days early warning. This is the DSS I was talking about. We have got the meteorological information communication system. It is again geo-enabled. That is geospatial technology is utilized here, and geospatial interpolation are carried out to find out the spatial mapping of various types of weather phenomena, starting with simple temperature, pressure, and wind, up to the cyclones, thunderstorms, heat waves, etc. Then we have data information processing system. It is mainly the R&D system, you can say. Then we have got the synthesized integrated visualization system, where we visualize all the information with the help of the geospatial technology. Then we've got the climatological information management systems. We've got a past historical data starting from 1901, all data are digitized. So therefore, we've got a very good climatology. All these climatological parameters are available in geospatial platform. Then we've got weather information and forecasting system, where we prepare the weather information and it is given to the public. If you go to IMD website, you can find out geospatial page for specific modules are there for different types of severe weather informations. Then of course, we've got PWIS, that is public weather information system. At present, IMD's information goes as a text part, that is a graphics part, and also the WebGIS information. In the graphics, we have got WebGIS graphics and also we've got the QGIS graphics. So all the informations are redundant, therefore people can utilize any one information as per their choice. Now, if you just look at what is the importance of the satellite data, I want to say that I was a little earlier telling that 90% data in numerical models goes from satellite. So therefore, you can just imagine how important is the satellite. So this one, the next one is that if you look at the entire globe, you'll find that the water is dominating, that sea is dominating, and land cover is less. Therefore, you cannot take the observations of the sea. Therefore, only the satellite can help you. So therefore, the information received from satellite are very much important to monitor, especially the marine hazards, and of course, the land-based hazards. So conventional observations are primarily limited over the sea areas. Okay, and therefore you have to depend upon the aircraft, ships, buoys, and satellites. The ships, buoys, and satellites are very limited in the sea area. Therefore, satellite covers more. So coverage is more. Therefore, we depend upon satellites more. Now let us look at data reception system. For example, in our modeling system in National Center for Meteorology and Weather Forecasting, we'll find that the various types of data comes off. All these data are the free flow. Also, data goes from IMD and various agencies across the globe. And as you can find out, the data are maximum from the satellites, including the geostationary satellites, the polar satellites like scatterometers, etc. Now, this is the Delhi Observation Report of Numerical Regression Model Simulation. This is just an example of 20 October 2021 to give you a feeling how much data we get across the globe. All data are collected, and almost within 10 minutes of the observations, we get all the data from the globe because of the high power communication systems. And all these data are plotted and analyzed in a geospatial platform. At the same time, all these data are included in the numerical modeling system. So this is again just an example in how much data are coming up and which is the most important data and which is the most useful data. This 3 years example is shown here. And again, satellite dominates. Of course, the temp data, that is the data from radio and radio wind observations, are also very important to improve the weather forecast. Now, this is the impact-based forecast. When we talk of the impact-based forecast, their weather information is converted into impact estimation and hence the response scenarios. At the same time, what we do actually, weather analysis and forecast is carried out. Then we extract the relevant information from the weather forecast. Then we place it into the situational context. For example, if I am giving heavy rainfall warning for a city, the situational context will be different. For heavy rainfall warning for a building, he or she may not worry, but heavy rainfall warning for a slum area, they have to worry. People have to evacuate it. Therefore, the impact estimation is considered the situational context. And accordingly, the mitigation strategies are developed and impact-based forecast planning bulletins are generated. And it is done in collaboration with various agencies like geospatial agencies, here ISRO and many other agencies. Then also you've got state government for socioeconomic parameters. Then you've got secondary hazards like floods for Central Water Commission or landslides, for example, GSI. So it is a multi-institutional mechanism which is in place and which helps to assess the hazard, vulnerability, exposure, and risk with the help of the geospatial platform. Right-hand side is just an example of multi-hazard warning maps generated by IMD every day. Now, while we go for this impact-based forecasting, you need geospatial information about various parameters apart from weather parameters. Like, for example, administrative layers, you need state, district, city, ward boundaries, etc. Digital elevation model data, land use, land cover data, meteorological data, of course, I told you, climatological data, infrastructure layers like railways, road, buildings, etc. Then demographic data like population, livestock, etc. Major point of interest like school, college, hospital, airport, bus stand, whatever you feel. Then impact matrices for hazards to be generated. So that for a particular area, the specific situational context impacts can be provided. So these are the different types of activities which we carry out with the help of the geospatial technology to provide the impact-based forecast in this requirement. So this is just an example of hydrometeorology, how we are utilizing satellite-based rainfall and soil moisture products are generated for flash flood guidance bulletins. Satellite data and products are also useful in water resource management and flood and drought monitoring. The regular evaluation of satellite data and products and advancement of algorithms are also needed, which is carried out by ISRO Space Application Center and IMD together. This is the agrometeorology. There are many products from the geospatial technology which are utilized for agrometeorology. For example, satellite-derived rainfall, soil moisture, soil temperature, evapotranspiration, surface temperature, NDVI, net radiation products are very important for agromet advisory services. Now, the next one is the climatological applications. For example, people say about the El Nino, southern oscillations, or Indian Ocean dipole, which are very crucial for the large-scale processes, which influences monsoons, etc. So how to estimate that? We estimate that it is the sea area that we have to depend upon the satellite. The satellite provides the information, and in addition, certain basic observations taken of nearby decides the monitoring of El Nino, southern oscillations, IOD, etc. Sea surface temperature, oceanate content, like. So this is an example of ENSO, IOD, or MJO monitoring. Mid-June oscillations, it is an equatorial wave. It moves from west to east, and it influences the various types of weather parameters. So it is carried out with the help of this data collected from the satellites. Now this is the inside data sharing. We utilize the satellite data. It is shared with many people. We share the data with NOAA, JMA, WMO, GSIS, CGMS, Carnabat Service, UMET, etc. Many more. Similarly, we also have various stakeholders which utilize satellite data from IMD, like say environmental web, aviation, defense, research, power, transport, national state authorities, tourism, many more. It is just mentioned here. So continued data sharing through a memorandum of understanding towards early warning for all for Southeastern region. That is what we carry out to ensure the availability of the geospatial data. Now, with all these developments, we have come up a long way. But however, still there are certain gap areas. So one of the gap areas is that the finer spatial and temporal resolution of geostationary satellite data. We do not have finer spatial resolution. We have to improve the spatial and temporal resolution of the geostationary satellites over South Asian region, so that we can have the better information about the flash floods, cloud bursts, lightning, etc., which cannot be detected by the existing satellites. In addition, for example, upper air turbulence, presence of cirrus clouds, fog depth, etc., are other weather events which are not monitored by the satellite at present. Constellation of satellite scatterometers, which is not available here in this world. One scatterometer cannot help to have continuous monitoring of the information over the oceanic areas. We do not have the information about the mean sea level pressure from the satellite-based information. The global all-weather vertical profile of wind, temperature, humidity at finer spatial and temporal and vertical resolutions are important for numerical prediction modeling, and hence towards the fulfillment of early warning for all. So this is where we lag behind certain countries. We have to work towards that. Constellation of cloud and precipitation radars for better understanding of the three-dimensional cloud or precipitation processes for further advancement for NWB models is also essential. Now, if we look at the global support, what we have apart from Indian space organizations and what support we provide globally, you will find that we have the collaboration with UN SPIDER, that is the United Nations platform for space-based information for disaster management and emergency response. We have got international charter space and major disasters to ensure satellite-based data made available globally during the disasters. And for this purpose, we have got the European Space Agency, French Space Agency, Indian Space Organizations, IMD, etc. The satellites like Landsat, Copernicus, and NOAA observe and measure physical, chemical, and biological properties on the Earth. ESA, Sentinel-1, and synthetic aperture radars to map water levels in rivers and flood-prone areas. We have the gravity recovery and climate experiment, the GRACE satellites to help track groundwater levels, which are critical in forecasting potential floods. The SMAP, that is the soil moisture active, phase, passive satellite, and MODIS tracks soil moisture globally. It also helps the these are the early indicators of the drought conditions. Global precipitation data or maps helps to assess the vulnerable areas. We have Indo-European ESM estimation, then also global risk assessment with the help of all this data. So if you just look at the emerging technologies, we have the artificial intelligence and machine learning. Combined with satellite data, AI can predict disaster trends, identify vulnerable regions, and enhance early warning systems. Coming up the CubeSats, small, cost-effective satellites will make monitoring more accessible for developing countries. And IoT integration, connecting space-based data with ground sensors can enhance real-time monitoring and disaster response. Geo or LEO missions can merge the gap areas of the information. The global hydrological mapping will be another step where the technology is coming up. So these are the emerging technologies which can lead us to the future when you move in this Amrit Kal towards 2047. There are challenges like data accuracy and resolution. I was telling you earlier also. Despite improvement, satellite data resolution may still be insufficient for very localized disaster monitoring. Interoperability, different satellites provide various types of data, which may not always be compatible to use or easy to integrate into disaster management system or even the multi-hazard early warning systems. The satellite data may not be in the desired format for integration into DSS. Cost and accessibility, high-tech satellite systems can be expensive to operate and maintain, limiting access to some regions, particularly developing countries. Many countries don't have the capability for the satellites. Then we have got the opportunities also because we have got World Weather Watch and Global Framework for Climate Services, which ensures effective use of satellite data in improving weather and climate services. WMO Integrated Global Observation Systems, WIGOS. Also, AMSET, improving the satellite data, core data, capacity building, and systematic observations financial facility and country support initiative to help the poor countries like small and nations, least developed countries to have the early warning system. Observing system capability analysis and review tool like WOSCAR tools further enhances the global analysis of space-based remote sensing data. International standards and guidelines for space-based disaster monitoring, ensuring that space technologies can be used consistently and reliably across different regions. Now, if I look at the requirement immediately, then I feel the fourth generation geostationary satellite, which is being planned by Indian space organizations, will be a major boost in addressing the gaps and opportunities. Polar satellites in minimum 3 orbits, collaboration with other agencies will be required. Space-based active instruments like LiDAR, radar for wind, water vapor, temperature, cloud, and aerosol profiles, and soil moisture. Multiple scatterometers, hyperspectral sensors, and lightning mapping sensors on board geostationary satellites. Constellation of small satellites. Ultimate objective, I'll tell you, is that we should have a three-dimensional continuous profile of the vital parameters like temperature, humidity, and wind in atmosphere, and current, salinity, and sea surface temperature in the ocean. These are the important parameters which are assimilated in numerical representation models, and these parameters can improve the weather forecasting. So with this, I'll stop here, and thank you very much for giving an opportunity. If you have any questions, I'll be happy to answer. Thank you.
Yes, sir. Thank you very much, sir, for your very information-packed talk. Sir, the question and answers are actually there in the Q&A tab. I will read it out, sir. There are 3 questions already. One is by Aniket Chakrabarti. He says that regarding the definition of heavy rainfall as defined by IMD, since the impact of heavy rainfall event depends on the location of the event. For example, the impact of a 64.5 millimeter per day rainfall event over Cherrapunji will be different from the impact of such event over Delhi or Jodhpur. So do we need a separate definition of heavy and extreme rainfall events for impact studies?
Yeah, so thank you very much, Dr. Aniket. We have different definitions: heavy rainfall, very heavy rainfall, extreme heavy rainfall. Like say 7 to 11 centimeters is heavy, 12 to 20 is very heavy, and 21 and above is extremely heavy. Then also we have got a criteria for exceptionally heavy. But I agree with you that, say for example, even the extremely heavy rainfall of 30 centimeter in Cherrapunji will not have that impact if you have got 30 centimeter in Jaipur and Rajasthan. Completely different. Therefore, that is the concept of the impact-based forecasting. So we have got the yellow, orange, red color impact forecasting, geospatial mapping. Here comes the role of geospatial mapping. We do it, but it needs a lot of data, as I presented in my talk. You need socioeconomic data about the city or the town or the village. You need data on the secondary hazards like the landslides or floodings, etc. Then finally, you can have the inundation mapping. We do not have a very realistic inundation mapping at present. Of course, we have got from NRSC some kind of inundation mapping that is post-analysis. But prior to that, we have come up with inundation mapping at the coastal areas for the cyclones. We have got inundation mapping for the flash flood guidance. But inundation mapping is not at present available countrywide by the Nodal Agency, Central Water Commission, or by IMD, or by ISRO. So we have to work together. I think CWC is also working towards those directions, and we are also developing that impact-based forecast. That once you calculate the inundation mapping, the height of total water, that will help you to quantify the vulnerability and hence the risk. And at that time, it will be immaterial whether it is 30 centimeter or 5 centimeter, 10 centimeter. If 10 centimeter rainfall is causing inundation, that has to be taken care. If 30 centimeter is not causing inundation, it need not to be taken care. So I agree with you that we have to go a long way to improve further. But however, taking into consideration all this feedback what we get, for last 2-3 years, we have introduced, addition to this 5, 10, whatever I told you, the 7, 12, and 21 as heavy, very even extremely heavy. We have introduced for the hilly areas, even 5 centimeter is considered as heavy. Similarly, for the urban areas, we consider even 5 centimeter as heavy. Depending upon the population density, depending upon the infrastructure, we also go for that type of specific criteria for specific areas.
Thank you, sir. Yeah. There is one more question by Dr. Biplav. He says that as the atmosphere is warming, are we going to get more lightning in the days to come?
Yeah, that's right. There are many studies towards that. Because of this global warming, you have got a changed environment. And if you look at the lightning occurs in association with thunderstorms. And the 4 criteria what we have for development of thunderstorm is that first one is that intense heating. The place should be intensely hot, say in the pre-monsoon season. Second one is the moisture. There should be low level moisture. The third one is that there should be conditional instability in the atmosphere. And fourth one is that there should be a triggering mechanism. So therefore, when you have got global warming, there is a rise in temperature in the country by 0.67 degrees Celsius past 100 years. In certain specific areas, it can be more than 1 degree Celsius. So that background heating makes the environment more favorable for occurrence of thunderstorms, keeping everything safe. The second point is that with the increase in temperature of 1 degree Celsius, there is increase in moisture by about, that relative humidity by about 7%. So therefore, now the environment will become more warm and more humid also. So therefore, you can expect the intense thunderstorms. The lower level pumping of moisture along with heating and at the upper level cooling becomes more favorable for intense thunderstorm activity. And as for global warming, the temperature is rising in lower levels, not in upper levels. Upper level temperature is falling. So therefore, the atmosphere is becoming more favorable for intense thunderstorm activity and hence the lightning. And lightning especially depends upon what? It depends upon the ice particles in the cloud, if though it is very deep, and if there's cooling at the upper troposphere, middle troposphere, then ice particles become higher, and lower level you got the warm water particles, and therefore there is possibility of more occurrence of the intense thunderstorms and lightnings. So we can expect, but it cannot be generalized for everywhere. It needs to be studied, and there are some studies. The certain pockets it shows also reduced activity in certain areas. And in general, there is increase in lightning activity.
So should we? There are 3-4 more questions. Should we take, sir?
Yes, I can take. Yeah. I can take.
There is one question by Dr. Nallaswamy Rajathinam. Sir is asking that for filling the gaps, how many new radars likely, especially to track cloudburst?
I don't know whether it will be possible to track cloudburst or not, but we hope that we will have the mechanism with the radar to monitor the cloudburst. Prediction may or may not, but monitoring. The monitoring of the echoes, the reflectivity in the deep convective clouds will be possible with the densification of the radars. At present, we have got 40 radars, and we are planning for 53 new radars in the mission Mausam, and order is in place for 34 radars. So total it will be 126 radars. So with the 126 radars, we will have redundancy. If one radar goes out, there is another radar which will be working. And also it will be covering various parts of the entire country will be covered, and additionally coastal area will be covered. And also the neighboring countries also will be covered to some extent. So that will help. But if you look at the hills like Himalayas, so there are so many hill peaks that you need many more number of radars to go over. But it is not possible to put up all these radars. Therefore, satellite, the geospatial technology will be very much helpful for that. But we have to improve, therefore, the satellite resolution. We have to improve, therefore, the polar satellites, CubeSats, etc., which can help us in the remote areas like the hills and remote areas like the oceans, etc., where the human being may not be possible for the human being to go and establish the observatories and to establish the radar station. Because to put up a radar, you need a road, you need a transport, you need a communication facility. So all these facilities should be available, but may not be available in the high regions of the Himalayas. So where you can get these informations with the improved resolution, improved accuracy of the satellite.
Yes. So on this accuracy only, there is one question by Dr. Abudi Subbarao. So he says, what is the accuracy level of forecast provided under Har Ghar Mausam? Can it be advisable to farmers in our awareness programs?
Yeah, in the awareness programs, we can inform the farmers. At present, we have established the forecast at panchayat level. So, but we do not have the model at panchayat level. The model is developed at the 12-kilometer resolution. Therefore, it can provide you forecast at the block level. But we are downscaling and providing forecast at the panchayat level. So what is the way forward? We have to go for a modeling system where we will have resolution of 5 to 6 kilometers. That is what Minister of Earth Science is planning during next 1 year. We will have the global model with a resolution of 5 to 6 kilometers and a regional model with a resolution of 1 kilometer. At present, regional model is run at 3 kilometer resolutions. Then for specific areas, for example, nowcasting of thunderstorms, heavy rainfall, etc., in hill areas and city areas, we are running the nowcast models with resolution of 2 kilometer and 1 kilometer. That has to go to sub-kilometer resolutions. And for this purpose, if you want to improve, say, for example, resolution by one step, you will require the computing power 6 times. Okay, therefore you need very high power computing systems. And recently, Minister of Earth Sciences has acquired now total is 28 petaflop machine, and it will certainly help. Now we are planning to have the high resolution models. Once these resolution models are in place, the forecast accuracy at panchayat level will improve further. We are expecting that 10 to 15% forecast accuracy will improve during next 5 years. And one thing is that on this mission Mausam, the detection will be very accurate for thunderstorms, localized heavy rainfall, etc. And also the nowcasting, the forecast, which is basically the extrapolation for next 3 hours, will be far better.
Yeah, I think, thank you, sir. These are the few questions, I mean, unique questions that we had. Aggarwal sir, Dr. Aggarwal sir is there, so I request sir to say a few words.
Yeah, Miss. First of all, on behalf of Indian Society of Remote Sensing and International Society of Photogrammetry and Remote Sensing Technical Commission 5 of WG4, I would like to thank Dr. Mahapatra sir. It was wonderful lecture. In fact, you started with Genesis. You started with the institutionalization of different segment of disaster risk reductions where our country is managing. And then you talk about that how meteorological predictions are there and how much improvement are there. This is really heartening to know that we have improved a lot. In fact, I can tell you, because we are also monitoring other countries predictions also. India's predictions are one of the best in the world, even in the developed country also, if you compare our prediction. And hats off to you and your team. You are known in our country as a weatherman or cyclone man. I know that. So thank you for, first of all, accepting our invitation. I know you are so busy, so tight. I discussed with your PA, and again, you have taken time and you could able to deliver a talk. And this talk is going to give a lot of information to our webinar series participants. And they are really, I'm sure they are very much benefited. In fact, I can see comments also. They are so much happy to hear from you. Thank you again, sir, for your kind time and delivering a wonderful lecture, which is going to be very, very useful to everyone. Thank you.
Thank you very much, Aggarwal sir. I feel honored with your nice words, and I once again thank all of you for giving me the opportunity. Thank you very much.
Thank you.
Thank you very much, sir. And I also thank Aggarwal sir for his continuous guidance and Lakshmi for the support. And I just for the participants here, we have an announcement that we had two more lectures scheduled in this series on 21 and 28, but because of the speakers' engagement, other engagements, they requested for a delay. I mean, for rescheduling the talk. So we are working with them. As soon as we get new dates, we will update. So we hope to see you there also. And thank you all once again. Have a good day. Thank you, sir.